Okay, and we are live. Welcome back, everyone. Today is our second to last live stream for Physics 8B. We're going to talk about interference and diffraction. Next week, we're going to talk about quantum physics. And after that, it's going to be dead week in the final, so it's going to come real quick, and then we'll be done for the semester. So there is light at the end of the tunnel. Today we have to talk about the other, in a sense, the other half of the story of light. I mean, we talked about optics last week, and that was just ray tracing, and we just thought of light in geometric terms, really. We just said we have a ray model for light, and we do ray tracing, and we can find where the image forms and where all that, you know, is it virtual, is it enlarged, whatever. And so that is fine, and it works very well, and it neglects entirely the fact that light is a wave. But we said, okay, well, if we're going to do that, fine, but then we do have to circle back and talk about the fact that light is a wave, and therefore light will, under certain conditions, display very specific properties that we did not cover in optics. And so that is the point of this chapter. Now, it's not a hard chapter from the point of view of math. It's a hard chapter conceptually. Part of the reason is that we could spend a lot more time than we do on this specific chapter. It's probably worth, 3 or 4 weeks if you really want to be thorough and cover the whole thing, but we do it maybe in less than one. So that's part of the problem. The other part of the problem is that we don't show you the kind of the macro view and the common, I don't know about the common denominator, but the common thread across the different topics that we present. And it tends to be just a checklist of topics and formulas, and it's like plug and chug, do this, do this, do this, do this. Double slit interference, these are the formulas. Single slit diffraction, these are the formulas. And we don't really try to give you a macro view of why we're doing what we're doing and what quantity is a common quantity across all these different experiments or situations that we describe. So that's what I'm going to try to do first. We're going to go quickly over waves and particularly constructive and destructive interference as a reminder. And then we're going to say, okay, well, what we are going to focus on in this chapter is path length difference between two waves. And path length difference is going to be something that in some cases we can actually compute from scratch. In some cases we can't, but in all cases it's the starting point. The question is, do I compute it myself, or do I rely on a formula that is given to me in the textbook and I just apply it because it's really too complicated for me to compute it on my own? That's what we're dealing with. And that's the common thread across all these topics, is that we want to ascertain the path length difference between two rays of light or two waves that might be waves of light typically, usually from a laser or some source like that. So let's just talk about constructive and destructive interference first, and let's just be super clear that we will typically use a laser, although not exclusively, but let's just assume for the sake of argument today that we're using a laser. Now, I'm not claiming that I have a blue laser and a red laser. I'm claiming that I have one single laser, whatever the color, let's say red, but I chose to draw two waves with different colors to track them separately, okay? And I want to start with the situation where these two waves, when they leave the laser, they're in sync, right? Or we'll say in phase, but it means in sync or in step. And they max out at the same time, they hit their min at the same time, right? If you were to slide one on top of the other, they would exactly superpose each other. And these waves are said to be in phase. Okay, now if two waves are in phase, when they leave the laser, perhaps they are not in phase when, let's say, they reach the screen where you want to observe some interference pattern, just for example. So let's say we have two slits, one here and one here, and part of the laser light that is blue is going to go through the top slit, and part of it that is red is going to go through the bottom slit. Again, blue and red is just to keep track of slits. It's not the color of the light. But the point is they start out exactly in phase because they come from the same source of coherent light. But if you want to observe what happens here on the screen, then they don't travel the same distance in the air, right? And so even though they start out in phase, they're not going to arrive at the screen in phase. In fact, the red wave is probably going to be slightly late to the party. The question is how late? And of course that depends on how much longer this is compared to this. Okay. Now how much is the red wave shifted compared to the blue wave? Well, that's going to be called the path length difference. Now really the path length difference is difference in length between this path and this path, but what it amounts for in the end is how much the two waves are shifted, right? So you could say, well, you know, they started out like this, but really, you know, when they got to the laser, they were like that. They're still in phase, but, you know, they used to be lining up right here, but now, you know, they line up like this. But okay, yeah, they're still in phase. Now, by what amount are the two patterns shifted? Well, that's going to be called delta x. And delta x is called the path length difference. Now, sometimes it's called little delta, like this, same thing. The point is, it tells you how much longer this path is compared to this one, and at the end of the day, it tells you how shifted your blue wave is relative to your red wave. Okay, now, of course, you could argue that we could describe any amount of shift, right? I mean, they could just be shifted super slightly. Maybe it's just that they're shifted this amount, like hardly at all, right? Or how about this? Or anything in between here and here really would be okay. And that's true. We're just going to focus on a shift between the two that results in the waves being exactly in phase again or exactly out of phase. Now, if they're exactly in phase again, like it is the case here, we're going to get constructive interference, right? And so constructive interference is going to mean that these two waves are going to combine in such a way that you get more light. In other words, you get a bright fringe, if you want to think of it in those terms, but you get light that is brighter than the individual light from each wave, if you want to think of it that way, because they combine together and give you more light. Now, what does that look like on, you know, if you were to kind of look at the form of the wave? Well, you would have a wave, you know, maybe it starts out like this, right? Let me do it here. Okay, and now I'll change colors just for clarity. Now you get a wave that has the same frequency but has double the amplitude, because you have two waves that have combined into one and they have the same frequency, but their amplitudes are going to add. And so now, instead of just getting a blue wave with an amplitude A, I get this purple wave, let's call it, with an amplitude 2A, right? And so I'm going to put this over here, right, just to say that, okay, this is going to be constructive interference. You get a wave that has the same frequency but double the amplitude, which means a brighter amount of light. Okay. Now, this is going to be something that happens when the two waves are shifted relative to each other, an amount delta x that is either equal to one full wavelength, or could be two full wavelengths. After all, if you did this, they would still be in sync, right? Where'd it go? There we go, like that. Or 3 or 4 or 5 or whatever. Any integer number of wavelengths for delta x is going to cause the waves to shift but end up in phase again. And so a condition for constructive interference is that delta x is equal to m times lambda, where m is 0 plus or minus 1, plus or minus 2, etc. Okay, and the question is, for a given situation, whether it's interference on a screen or thin film interference or whatever, can I compute delta x and then say whether it's equal to m lambda or the destructive interference condition that we're going to derive next? Or am I given delta x and then I just deal with it? But the key is delta x. Across everything we're going to do, we're going to be worried about either figuring out what delta x is on our own or using a formula that's given to us because it's too complicated for us to find delta x. Okay, so then let's entertain the other possibility, right? Where these two waves leave in sync. Okay, they go through different slits, they travel different distances, and now they arrive shifted in such a way that when the red wave is max, the blue wave is min, and so on and so forth. Okay, so now they used to line up right here, but now it's like this, and they're shifted an amount, delta x, but delta x is not going to be equal to an integer multiple of wavelengths. It's going to be either maybe half a wavelength or 1.5 wavelengths, 2.5, and so on and so forth. And if that happens, then you get destructive interference. And if you get destructive interference, the two waves cancel each other out, and you get no light whatsoever. You get a dark fringe because they exactly cancel each other out. If you add these two together, right, when this is max, this is min, those two cancel out. When this is min, this is max, those two cancel out. And so you get destructive interference and therefore a dark fringe. In other words, the absence of light. So destructive interference. Okay. Now, you are going to get destructive interference when delta x, the path length difference between the two waves, is equal to, well, either half a wavelength or 1.5 wavelengths, 2.5, 3.5, and so on and so forth, which we tend to write like this, m plus 1/2 times lambda, where m is 0, plus or minus 1, plus or minus 2, and so on and so forth. All right, so that is for destructive interference. Now keep in mind that what we're going to do now is we're going to go through three different experiments or phenomena that we're going to, for which rather we are going to either derive delta x or use a formula. And then from there we will know what type of interference we observe. Do we observe constructive or destructive interference? Does that mean bright fringes or dark fringes, and so on? Now, we are going to go in the following order. We are going to go from the situation where we can fully compute delta x on our own and it is expected that we do so. That's thin film interference. Then we're going to move on to double slit interference, for which we have a few assumptions that underpin how we compute the path length difference, but we're still able to compute it. And then we go on to single slit diffraction, and at that point we're going to just throw our arms up in the air and say, you know what, I don't know how to find delta x, the path length difference. Why don't you tell me what the formula is, and I'll just apply the formula. Okay, but that's the common thread across these three topics. Okay, so let's first talk about thin film interference, and perhaps we ought to clarify what we mean by thin film interference at first. Now let me draw a thin film, which it's not going to look thin, but let's just understand that in reality this is something extremely thin, typically on the order of microns or nanometers, right? So it's a very, very thin film of some transparent medium that has some thickness T and an index of refraction, call it, I don't know, N2. Okay, and let's say that this is N1. Now N1 is typically air. I'm just going to call it N1. And we are going to assume in this case that we have N1 on the other side. Doesn't have to be the case. Your thin film could be resting on a piece of glass with an index of refraction N3. That's different. But I'm just going to assume that this is a thin film of soap. And the reason for that is that that's a relatable thing that you've experienced in everyday life, where if you have ever observed soapy water or soap bubble, you've seen these colorful swirls over the surface of the bubble. Now, these colorful swirls come from the fact that the thickness of the bubble varies throughout the bubble. And in general, what you keep in mind for thin film interference is that a specific color corresponds to a specific thickness. And so if you see a red swirl, well, that thickness right there is just the right thickness for red light to interfere constructively, but not the other lights, not the other wavelengths perhaps. And same thing if it's a blue swirl instead. But that's a very important thing to keep in mind conceptually, is that thin film interference is going to be the interference that you get because the thickness of the film is such that it will allow one wavelength to interfere, and it will give you, let's say, a red color, and therefore a given color corresponds to a given film thickness. Now, sometimes the films that we study will have a constant thickness, and therefore there's only one or a few lambdas that are going to work, or sometimes these films are going to have thicknesses that vary, and then different wavelengths are going to work at different locations, and you might see colored bands like a rainbow or something like that. But the point is, for a given color, you have a given thickness. Okay, so there's a few things, actually a lot of things we have to talk about when it comes to thin film interference. This is the hardest type of problem because it requires the most initiative on your part. And let's start by saying that what we typically do is shine light on a film like this. Let's call it a soap film. And we typically observe the film from the same side that the light is coming. So we'll shine light like this, it'll bounce off and it'll hit your eye. Doesn't have to be the case. You can observe it from the other side. It makes things a little bit more complicated. You should have a look at old exams for that. But the principle is the same. We will shine light on this film. Some of the light, now all of the light is going to come in at what we say is quasi-normal incidence, which means basically perpendicular to the surface, or almost, very close. So light comes in like this. And then light is going to reflect in part off the top of the film. So some of the light is going to reflect off the top of the film, but some of the light is going to enter the film and reflect off the back of the film and then come back out. And of course, some of the light's going to go through, but we don't care because we're observing it from above, so we want the light that's reflected back up. Okay, now if I draw this is complete nonsense. Like, this is a shit show. I don't know what ray is what. I can't track if one part of the light traveled more distance than the other. So yes, this is actually how we shine the light, and we always say that in problems, that it's quasi-normal incidence. But in practice, that's never how we draw stuff, because this is nonsensical. I can't do anything with this. So instead what we do is this. We will draw. And again, blue and red is just to tell the rays apart. It doesn't mean that we have red and blue light. But I will start with the blue ray. The blue ray is the portion of the light that is going to reflect off of the top of the film. I'm going to call this ray number 1. And then some of the light is actually going to enter the film and reflect off the back of the film. Okay, now I draw these rays like this slanted, even though they're supposed to all be vertical, because otherwise I can't tell the two rays apart. Okay, this is going to be ray number 2. And because ray number 2 had to travel a distance that's a little longer than ray number 1, it arrives right here, shifted compared to ray 1. And that means that we will see either constructive interference, so maybe a red swirl or a purple swirl or whatever, or destructive interference, which means we will see nothing at all. There will be no reflection, which might be the case, for instance, for an anti-reflective coating, right? You might want that. You might want no reflection. On the other hand, butterfly wings, the reason they shimmer is because, well, within that thickness of the wing, you get thin film interference, and for the right thickness, you get these different colors. And so this is the same idea as the soap bubble. Different thicknesses will give you different colorful swirls, or like colors that shimmer in the case of a butterfly wing. So that is what thin film interference is about, and I stress again that these films are incredibly thin, and it's fine because the wavelengths that we deal with are incredibly small. I mean, they're on the order of the hundreds of nanometers. So, you know, even if this is a micron, that's actually a lot compared to 100 nanometers. It's 10 times, you know, the wavelength. So, with that said, we draw the rays like this, even though they travel vertically, because at least now we can tell them apart. And then we need to do a couple things to account for the fact that, number one, not all reflections are made equal. We're going to have to talk about that. Number two, the wavelength that we're going to care about is the wavelength measured in the film, which means that I'm going to call this lambda 1 for the light that's traveling in air, and usually that's what you're given. Okay, we'll tell you, oh, red light is, 700 nanometers or whatever. Well, yeah, it's 700 nanometers in air, but red light in water is not 700 nanometers. The wavelength changes. And so the wavelength as measured within the film is going to be lambda 2. Now, it's fundamentally important to remember that it is the wavelength in the film that we care about, not the wavelength in air. When we write our condition for constructive or destructive interference, the lambda that we put in that equation is lambda film. And we get lambda film from lambda 1 by writing n1, lambda 1 is n2, lambda 2. In other words, that lambda 2 is n1 lambda 1 divided by n2. And more often than not, n1 is 1 because it's air, and so you just get lambda 1 over n2. But you have to use the proper wavelength when you're writing your constructive and destructive interference conditions. So that's one thing. The other thing is, as I said, not all reflections are made equal. And so if we have some medium here where n2 is less than n1, for instance, whereas here we have n2 is greater than n1, then as the light reflects off of this interface, you are either going to incur a phase shift or no. And what that means is you're going to incur an additional path length difference or no. So I'm not going to spend too much time on this, but here what's going to happen if n2 is less than n1 is that there is no phase shift. In other words, we're going to write delta equals to 0, meaning that there's no additional path length difference to account for. However, if you reflect off of a medium that has an index of refraction n2 that's greater than n1, then light will undergo a phase shift. And it will appear as if light had traveled an additional distance, lambda over 2. It didn't really travel more distance when it reflected, obviously, right? In these two cases, obviously, we're talking the same distance traveled upon reflection, but by getting the phase shift, it basically flips your wave. If it was one way, it flips it the other, right? If it came in like this, it leaves like this. No, come on. It leaves like this. So it flips the wave. And so it's as if the wave had been, if you've taken it and moved half a wavelength in one direction. And so what we say is that you have an additional path length difference delta, which is going to be, now careful, lambda 2 over 2. Okay, so half a wavelength more. So we'll say that it is as if wave had traveled an additional distance delta. Okay. Now, you can more or less just memorize that, because I'm trying to do here is just plant the seed that we have to evaluate the different reflections that we have. We're not trying to fully understand why a wave would behave like that upon reflection. Let's just kind of memorize it. And what's going to matter is that when we go have a closer look here, we decide whether we have a phase shift or not upon reflection. Now, ray number 1 is going to reflect off a medium with index of refraction n2. I'm going to go ahead and assume that n2 is greater than n1. I don't have to do that. It doesn't have to be the case. And that's why you should be careful, because, again, thin film interference, everything is on you. You have to drive everything, and there's plenty of different variations that we can make to the problem so that it doesn't look exactly like the previous problem you did. One of them is how n2 compares to n1. The other one is whether here this is n1 or n3, and how n3 compares to n2, and so on and so forth. We can change the thickness of the film or not, and so there's a lot of parameters that can change, but the approach is going to be the same. You identify your reflections here, and we're going to say that here there's going to be a phase shift because we reflect off of n2 greater than n1. So for ray number 1, we're going to get plus lambda 2 over 2. Okay? And then for ray number 2, in this case, we are reflecting off of n1. n1 is less than n2. There's no phase shift here. So nothing to worry about. Okay. So now that I've said that, we need to figure out the path length difference between ray number 1 and ray number 2. All right. Now, the path length difference between the two is going to be in part how much more distance did ray number 2 travel compared to ray number 1, but I need to incorporate my phase shifts when I have them. So I've come up with a method over the years of teaching this and trying to figure out something that kind of always works, or at least is systematic, where, I mean, if you approach it this way, you should always get the right delta x. Now, what I'm going to do is the following. I'm going to say that delta x is going to be L2, and L2, just for clarity, is the length of this path. If I took a ruler and I measured this path, that would be L2. I'm going to put plus, and I'm going to leave a placeholder, and we'll talk about that in a second, minus L1. L1 is the length of the path followed by the blue ray. Plus, I'll leave a placeholder here like this. Now, in theory, forgetting anything about phase shifts upon reflection, it ought to be the case that if I measure L2 and I subtract L1, I get the path length difference between rays 1 and 2. But because of the path length difference, or the phase shift upon reflection is what I meant to say, then I have to look at each ray separately and say, oh, do I add delta or not? Okay, so ray number 2 undergoes 1 reflection. There is no phase shift here, so I'm just going to write 0 here. However, ray number 1 undergoes a phase shift during its reflection, meaning that it is as if ray number 1 had traveled an additional distance, lambda 2 over 2. So I'm going to add that to L1. Okay, so it's not actually the case that L1 is longer by that amount. It is as if it were because of the phase shift. Okay, and so then this is going to be L2 minus L1 minus lambda 2 over 2. Okay, fine. L2 minus L1, hopefully everybody agrees, that is now in fact the difference between this length here and this length here. That distance should be 2 times the film thickness. Okay, remember, I'm drawing my rays slanted for convenience, but they're all vertical, right? They all come in like this and then reflect off. So how much more distance did ray number 2 travel in the film? 1 thickness down, 1 thickness up. That's 2t, And so this is going to be L2 minus L1 is 2t minus lambda 2 over 2. There we go. So that's my delta x. And then I can say, oh, well, what do you want? Are you telling me that I see a colorful swirl here? Then I'll say constructive interference and I'll write delta x as m lambda. Or do you say, oh no, the film is an anti-reflective coating, it appears black, and then I'll say delta x is m plus 1/2 lambda, I get destructive interference. But that's easy because once I know delta x, I can either set it to m lambda or m plus 1/2 lambda, depending on what I'm told I observe on the film. Or what I want to observe on the film. Anyway, the point is, what's hard about thin film interference is finding delta, because it hinges on a whole bunch of different things, right? First of all, you have to remember this. Second of all, you have to account for reflections, which means that you have to draw your rays properly. Then you have to worry about how n1 compares to n2, and whether this is n1 or n3, etc., etc. And so there's all these different parameters that we can tweak to make a problem that looks like this one, but is different enough that you're not going to get the same delta x. That I don't want to box this delta x because I don't want you to think that it's always going to be that. Instead, I would rather that you understand how I got it, and then you'd be able to do it for any thin film interference problem you're going to get. But more likely than not, you will get a different delta x if you do a different thin film interference problem, even though this is a very common scenario. Okay, so that's all I'm going to say about this for now, because I want to be able to go do a problem and then just solve it, and then we can, in the problem, set delta x equal to m lambda or m plus 1/2 lambda or whatever. But I wanted us to have the tools to know how to find delta x for thin film interference. And again, the point in all of these different experiments that we're going to talk about is to know what delta x is, either because you find it or because you derive it. So we've talked about thin film interference. Let's talk about the next one up. The next one up is double slit interference. And so you have two slits and you shine light from your laser onto these two slits, right? It has a wavelength lambda. And double slit interference is also called Young's experiment. Makes a few assumptions. First of all, it makes an assumption that all we care about is the spacing between the two slits, and that the slits are infinitely narrow. In other words, we don't worry about the width of the slits. Now that seems weird because you're like, excuse me, if the slit has no width, then light does not go through the slit, so what's going on? Okay, fair enough. Think of it this way, right? It's an idealization. Think of it as a line of light. But when I say line, I mean a mathematical line, right? It has no thickness. What is the thickness of a mathematical line? It doesn't even make sense. It doesn't have one, right? So it's an idealization where you take the slits to be so thin that you neglect anything that has to do with their thickness or their width. And that simplifies things quite a bit. What you get is not what you expect, because you would probably expect, if you shine a light through two slits like this, to get boom, boom, two slits of light, two red slits like that, or two red fringes, I should say. Why would you get anything else? There's only two slits, so you should get two fringes. But that's not what you get at all. You get this collection of fringes. You get alternating bright and dark fringes with the same brightness and the same spacing all throughout. And that's unexpected because you're like, well, how did that happen from only, shining light on two slits? But then if you think about it, you kind of go back to what we said earlier, and that's the fact that, light coming out of the top slit is not going to travel the same distance as light coming out of the bottom slit. And so, the waves are going to reach the screen shifted, and sometimes they're shifted the right amount that you get a bright fringe, and sometimes they're shifted the right amount that you get a dark fringe, and then it starts over because if you shift a little more, it becomes a bright fringe again. And so the idea is that this fringe here, be it bright or dark, is going to be located at an angle theta, or equivalently a coordinate y from the center. And all the fringes have the same brightness, the pattern is centered on a bright fringe called the bright central fringe. And if you were to plot the brightness of these fringes, you would see something like this. You would get equal brightness, equal width. Okay, this is a little sloppy, but you're going to see that it's very different from what I'm going to draw for single slit diffraction. So for double slit interference, if you can assume that the width of the slits does not matter, then you get alternating bright and dark fringes with the same brightness and the same width all throughout the pattern. And the question is, can you evaluate delta x, which is how much more did this ray travel compared to this ray, so that I can know what delta x is, and I can then set it equal to m lambda or m plus 1/2 lambda to find my fringes. Okay, so we're going to do that, and that's where another assumption comes into play. So here's our setup, right? Viewed from above, we have these two slits and the fringes on the screen and all of that, and that's all fine. Put this here. And let me do this. I'm going to erase this for now. Let me actually move the screen back just for convenience. Right? It's going to be easier to see what's going on. Now there's going to be this guy here. There you go. That's the bottom, and that's the top. Okay, and this is going to be the center, of course. All right. Okay, so then this is going to be a distance L1, this is going to be a distance L2, and delta x is simply equal to L2 minus L1. And what we're going to say is that this angle here is the angle that we use to reference what fringe we're talking about. It doesn't matter if it's a bright or dark fringe. If you tell me theta, I know where to look on the screen. Okay, and then it might be bright, it might be dark, but theta gives me position. Now, the light that we use is typically hundreds of nanometers, and the screen distance, L, is easily meters. I mean, you know, what, a few yards, maybe? So like 2 meters, call it. But it's in meters, and you know, 100 nanometers is what? It's like 10 to negative 7, so it's like 10 million times smaller, something like that. So because of it, to the light, in a sense, it's as if the screen were infinitely far away, right? Because the length that matters, that makes sense for the light, is the wavelength. And it's going to travel 2 meters. You're like, okay, well, that's pretty much infinitely far away for something, you know, that's measured in, what, 10 to negative 7 meters. And because of that, and remember optics, we're going to say that we can treat the rays as if they were leaving like this parallel to each other. Right? Now you're going to say, this is complete nonsense. If we do that, they're never going to converge here. It's like, okay, remember optics, yeah? It's like the railroad track. If you look down a railroad track, the two tracks don't intersect. I mean, duh, it would be a terrible railroad track if they did. They don't, but it looks like they do. And so something, you know, two parallel lines intersect at infinity in the world of optics. So what I should do is I shouldn't even draw the screen. I should just say, you know what, I'm just drawing the rays. I'm just zooming in like this, and as they leave, it's as if they left parallel. They're slightly not parallel so that they do converge on the screen, but it is as if they were parallel. Now the thing is, if I do that, and without spending too much time doing the derivation, I'm going to say that the difference between the two is only this little piece right here. If this is a right angle, this right here is going to be delta x. The bottom ray travels that much more compared to the top ray. And it turns out that right here I have a triangle that looks like this, and I'm going to blow it up because otherwise we can't see anything. But it's going to be a triangle where one side is D, the spacing between the slits.
The other one is whatever this needs to be. And then this piece here is delta x. Right? So I have, this is 90 degrees, and this is delta x. And you can do the geometry and convince yourself that this angle here will be theta, which is exactly this theta. And because of it, delta x is d sine theta. Now, if you don't know this, you're not going to go anywhere when it comes to double slit interference. And I only did the proof of the derivation to convince you that we could find d sine theta on our own. If we were to make a few assumptions, one of them is that the slits are infinitely thin. The other one is that we can treat the rays as if they left the slits parallel. And if you accept these assumptions that we made, then delta x is d sine theta. Now in practice, will you have to go find d sine theta in a problem? Probably not. You can actually just claim that it's d sine theta, but I prefer for you to see at least once where it comes from, because I said we're going to go through these problems, and as we go, we're going to be less and less able to compute delta x on our own. So it was technical but feasible for thin film interference. Here it's like, well, okay, it's feasible, but like with some assumptions, and it's not obvious how we would get d sine theta on our own, but fair enough, if you show me, I can understand where it comes from. And then single slit, I'm just going to tell you what delta x is, and we're not even going to try to make it make sense or explain how it's derived. So the point is, delta x for double slit interference is L2 minus L1. And then from there, you can locate the bright fringes and the dark fringes, right? The bright fringes are going to be located at delta x is equal to m lambda, which means that you're going to have d sine, I'll call it theta sub m, is equal to m lambda, for m equals 0, plus or minus 1, plus or minus 2, etc. Okay, so those are all the angles for which we are going to get bright fringes on the screen. There's more than one, right, because you could let m be any integer listed here. And then for dark fringes, well, the angles at which we're going to find dark fringes on the screen are going to be given by delta x is equal to m plus 1/2 of lambda. Okay, so that's d sine theta m is equal to m plus 1/2 of lambda. For m, same thing as 0 plus or minus 1 plus or minus 2, and so on and so forth. But you need to know that delta x is d sine theta, otherwise basically you're not going anywhere. All right, so then the last one is going to be single slit diffraction. This one is even weirder because at least when there were two slits, you could, argue that, oh, okay, well, part of the light goes through the top slit, part of the light goes through the bottom slit. They don't travel the same distance, so there's a delta x, good. Single slit diffraction is there's only one slit, so you're like how, why, like what's L2, what's L1? Aren't they the same thing? Is it just like this is L2 and equal to L1 right there? And fair enough, it's easy to see why you would think that. Let me get rid of this. That's from something else. There we go. What happens, just to keep it simple and give a semblance of explanation, is that now you have a slit that has a width, typically denoted by A, and you can't neglect that width because otherwise you have nothing. And you can think of it as light from the top half of the slit interferes with light from the bottom half of the slit as it goes through the slit. And that's why on the screen you get alternating bright and dark fringes. However, the bright central fringe is going to be the brightest and the widest. Okay? So you have to be careful that you get a pattern that looks the same, except if you were to plot the brightness of the pattern that you get, it would look something like this, right? And so you would get a bright central fringe, which is the brightest fringe of all. And in this case, it is very hard to find delta x, so we're not even going to try to do it. We are instead just going to say, you know what? We're not even going to give you delta x. We're just going to give you a formula for dark fringes. That's how complicated it is. So we're going to say dark fringes are located at the following angles. A, the slit width, sine of theta m, is equal to m times lambda, which seems weird because m lambda looks like it might be constructive interference. But you can kind of think of it as, light from the top half, with lambda over 2 here, so that you get destructive interference. The 2 goes away. That's not exactly it, but just to make peace with the fact that you get m lambda, or if you don't need to make peace, you just memorize it, then good for you. That's where the dark fringes are going to be located. We have to be very careful. We cannot have m be 0. If m is 0, this is 0, which means theta is 0, but theta is 0 is the bright central fringe, so you can't have that. So you can only have m is plus or minus 1, plus or minus 2, and so on. And that's going to be the angles at which dark fringes are located. So, like I said, as we go through the 3 cases, it gets worse and worse, and in the 3rd case, we don't know how to get this equation. And not that we couldn't understand it if we tried and we did the work, it's just, it adds nothing to your understanding. And what we want to do in this chapter is emphasize that there are these different types of experiments that are classic physics experiments that highlight some different phenomena. There's thin film, there's double slit interference, and then there's even single slit diffraction, meaning that you can get interference just with 1 slit, you don't need 2. And that's because the light interferes with itself, like half of it interferes with the other half in a sense. Okay, so then that's just going to be where our dark fringes are. And we're just going to memorize that for single slit diffraction, which means that for a single slit diffraction problem, I shouldn't get a question about, oh, where are the bright fringes? Like, really? Really? You're going to ask me where the bright fringes are? I can find them. Because, obviously, where are the bright fringes? They're in between the dark fringes. So I can find where the dark fringes are and be like, okay, now that I know where the dark fringes are, I can tell you where the bright fringes are. They're in between, and this is where they're located. But it's a dick move to ask about bright fringes when it comes to single slit diffraction. It's typically never the case. So you did something wrong if that's what you get on the exam. Like you all misbehaved as a group if someone writes an exam with single slit diffraction but asks about bright fringes instead of the dark ones. But it's doable. It's just tedious, but it's doable. Okay, so that's the bare bones, and I didn't want to spend too much time going over that because, again, the goal is kind of just to not repeat lecture and to bring to the surface what's important. These 3 topics are very important. You should understand them as best you can. And now we're going to do some problems to kind of see, okay, if you were to give me a problem, what would it look like and how would I apply what I just learned to set it up and solve. And we're going to do 3 problems. We're going to do a thinning soap fill problem. We're going to do double slit interference in different media, which is a good one. It's a fun one. And then we're going to do diffraction with blue and orange light, which is a phenomenal problem. Yeah, we're going to go through all 3. So here we have a soap film, kind of like we had before. We're given the index of refraction. Light comes in from the left, is going to reflect off the film, both the front and the back. And Louise, who's looking at the film from the left, sees whatever she sees. And we're going to determine if she sees the film as, colored red, or is the film look blue, or whatever. And
what happens is that in this problem, the thickness of the film is a function of time. Right? Now remember, one color corresponds to one thickness. If you start to vary thickness with time, you can anticipate that the color of the film will be a function of time. It's going to change throughout the problem. Okay? So whatever, we have a function here. This function, just to be clear, shows that the film decreases in thickness, right? It's going to start out with a thickness d0, but then as time increases, once you hit 100 here, you're going to get 100 over 100. That's going to be 1. You're going to have 0. The film will be gone. So eventually the film vanishes entirely, but we have 100 seconds worth of film to study what it looks like. Okay, so what is the thickness of the film d red in nanometers when it looks red? The wavelength of red light is 700 nanometers. Okay, well, let's set this thing up. Okay, now it's thin film interference. So what do I know? I want to draw my film, and yes, it's a thin film, but if I draw it wide enough, it's going to help me see what's going on and draw all the different rays. It's going to have a thickness d of t. This is going to be some index of refraction n, which is 2.5. Out here we're going to have n air, which is 1. Out here the same. And I care about how the indices n compare to each other because it dictates not only the wavelength in the film, but also whether I get some phase shift upon reflection or not. Okay, so this is my film getting thinner by the second. Okay, and Louise is over here looking at the film, and I shine light from the left, so I need light to reflect off the front and the back of the film and come back out to reach her eye. Okay, and I know that the light typically comes in like this at quasi-normal incidence. I even think that they tell you that. No, they don't, but they should have. But, okay, instead we're going to draw the light slanted enough so that we can tell what's going on. So this is going to be part of the light that's going to reflect off of the top of the film or the front of the film. That's going to be ray number 1. And then there's going to be the light that enters the film, reflects off the back of the film, and then comes back out and interferes with ray number 1. So it's going to come in like this, it's going to reflect like that, come out, and interfere with ray number 1. This is ray number 2. Okay, and what do I know? Well, I know a few things. I know that first of all, what I care about is wavelength in the film. So lambda SOAP is going to be, well, it's n air, lambda air, divided by n. And since n air is 1, this is just lambda measured in air divided by n. So the 700 nanometer for red light, that's measured in air. That's what I plug in here. But, I have to divide by n from the SOAP so that I get lambda measured in the SOAP. And then the other thing I have to worry about is phase shifts upon reflection, whether or not I get them. That depends on how my indices n air and n compare. So how many, 1, 2, 3, how many reflections, excuse me, 1 second. How many reflections do I have? Well, 2, 1 for each ray. Ray 1 here reflects off of a medium with an index of refraction n that is higher than the index of refraction from air. So here, ray 1 is going to incur an additional phase shift, which means it's going to be as if it had traveled an additional distance, lambda SOAP divided by 2. Okay, so there's a phase shift right here, which is equivalent to adding lambda SOAP over 2 to the length L1. And then over here, no phase shift. Okay, no phase shift, we reflect off of air. Air has a lower index of refraction, right? Because, well, just to be clear, like the ray is traveling through the SOAP film now, and it bounces off something
which is air that has a lower index of refraction, so then there's no phase shift for that refraction. There's no phase shift for that reflection. Speaking of which, by the way, as I twist my tongue, there is never a phase shift upon refraction. So when light enters here and exits here, there is no phase shift. It's not a thing. Phase shift only occurs sometimes upon reflection on the condition that you reflect off of a medium with a higher index of refraction. Okay, so we got ourselves lambda SOAP here, and let's find delta x. Delta x is going to be, let's use the method we discussed, it's going to be L2 plus, let's leave a placeholder, minus L1 plus, let's leave a placeholder. Now ray number 2 does not undergo a phase shift, so it's plus 0 here. Ray number 1 does, and it is as if ray number 1 had traveled an additional distance, lambda SOAP over 2. And so I'm going to add lambda SOAP over 2 here. And then I'm going to say, okay, well, this is L2 minus L1 minus lambda SOAP divided by 2. And L2 minus L1 is the difference between this entire distance here, if you measure it, and this one, if you measure it with the ruler. The only difference is that the red ray had to go one film thickness this way, one film thickness the other way to come back out, and therefore L2 minus L1 is 2 d of t minus lambda SOAP over 2. Okay, and actually I don't even need to know what the question I'm answering is to do this. This is the basic setup of a thin film problem. Okay, but the question is, what is the thickness of the film D red in nanometers when it looks red? Okay, well, let's go figure that out. I have delta x that's a function of the thickness of the film, right? And I'm going to say that the film looks red when I have the following. When delta x is equal to m times lambda red. Because if delta x is m lambda, then that's constructive interference. And so then it would make sense to see the film a certain color. Let's call it red. Now here's where you have to be careful. It's not really lambda red. It's lambda red measured in SOAP. Again, all the wavelengths for thin film interference have to be measured within the film. So it's not lambda red. It's lambda red divided by n. Just like here, we said lambda SOAP is lambda air over n. Okay, so as long as we're clear on that, and we were just careful with that, then we can say, okay, delta x is going to be m lambda red over n. What does that mean? Well, that means that 2 times d, let's call it d red, minus lambda SOAP is just lambda red over n. So this is over 2n, just to be clear, right? In case you're wondering what I'm doing, I'm saying lambda SOAP is lambda in air, which is red apparently, divided by n. That's the same formula we applied here. I mean, no different, but you have to plug it into here as well. Okay, so I need this to be m lambda red divided by n. Okay, so I need 2d red to be equal to m plus 1/2 lambda red over n. Okay, and I can divide by 2 for that matter, and I get this. And I know that it's for m is equal to, now d red has to be positive, right? So m, the smallest m could be a 0, 1, 2, 3, and so on and so forth. Now, how do I know which one to choose? I don't, right? I'm going to just try. I'm going to start with m is equal to 0, and I'm going to see what I get. I'm going to get d red is equal to lambda red divided by 4 times n. That's going to be 700 divided by 4 times 2.5, which is 10. This is 70 nanometers. Okay, well 70 nanometers works, yeah, because if you remember what we just said before, at t equals 0, the film thickness is d0. That's 100 nanometers. So it's going to go from 100 nanometers to 0. So as long as I'm within 100 nanometers, okay, I'm fine. So if I wait long enough, the film will thin down to 70 nanometers. It will then look red because one thickness corresponds to one color. Now, what happens if I, try m equals 1, because maybe there's more than one thickness that works? Okay, well, there is theoretically, but in practice, maybe that doesn't work out. So let's see. So this is 1 plus 1 half, which is 3 halves, of lambda red over 2n. This is 3 lambda red over 4n, which is basically 3 times this. That's 210 nanometers. Yeah, that would work, but that's greater than 100 nanometers, so basically we rule it out. And so the film thickness for which the film appears red is 70 nanometers. Right? That's our answer. Okay, and so then we can figure out, well, how long did it take for that to happen? Okay, so let's solve for t red, the time at which d of t is equal to d red. Okay, so if we do that, if we solve this thing, we're saying that we're solving d0, 1 minus t red over t0 times d red. Okay, so this is going to be 1 minus t red over t0 is d red over d0, and that's going to be t red, if you flip this around, so it's going to be t red over t0 is 1 minus d red over d0, and then if I just multiply both sides by t0, I'm going to get this, and so t red is going to be equal to t0 is 100, 1 minus 70 nanometers divided by 100 nanometers, so that's going to be 0.7, so 0.3 times 100 is 30 seconds. Okay, after 30 seconds, the thickness of the film is 70 nanometers, allowing red to interfere constructively, and therefore the film then appears red. Okay, and then, well, the third question is kind of bonus, right? It says, well, at what time T blue does it look blue? By the way, the wavelength of blue is 400 nanometers. Okay, so I mean, we just do the same thing, don't we? Okay, so for blue light, I mean, what's the difference? The only difference is that we're going to have lambda blue instead of lambda air, right? So we're going to find that d blue is going to be equal to, well, m plus 1 half lambda blue over n. Right? Now, if you write this, nobody's going to question you. Obviously, this is the beauty of variables. Like, the only difference is I swapped out lambda. So, okay, d blue is just the same formula as before. Instead of lambda red, we have lambda blue. That's all. And so for m is equal to 0, which is the smallest acceptable value, we're going to get d blue is equal to lambda blue divided by, no, I forgot one thing here. There's a 2 there, my bad. Divided by 4n, there we go, that's right. So that's 400 divided by 4 times 2.5, which is 10, so that's 40 nanometers. Okay. For m is equal to 1, just to check, now it's not going to work, but let's just convince ourselves. D blue is going to be, same as above, 3 lambda blue this time, over 4n. That's 3 times 40 is 120 nanometers. That's greater than 100 nanometers. So not possible, so we don't care about this. Our answer is that the film will appear blue when its thickness is 40 nanometers, and therefore I can solve for T blue. T blue is going to be, I'm just going to reuse this. The only difference is I have D blue instead of D red, so it's T0 multiplied by 1 minus D blue over D0. That's going to be 100 times 1 minus 40 over 100. That's 0.6 times 100 is 60 seconds. And 60 seconds is less than 100 seconds, so we're all good. Makes sense that 40 nanometers is still within 100 nanometers to 0, so it makes sense that you find a time that works too. And T blue is just 60 seconds. So really good little thin film interference problem there. Pretty classic, and with a nice twist where now the thickness of the film decreases as a function of time. Why not? Okay, so then let's go do a double slit interference problem, and we'll do it in 2 different media, right? So we are told that experiment A and experiment B are exactly the same experiments. We have 2 slits here, and this is Young's double slit experiment. So the slits have a width that we neglect, only matters that there's a spacing D0. There's a distance L0 to the screen, and we're using a certain wavelength, which is lambda, which is given. So lambda is the wavelength. Okay, that's in air. So this is air, and therefore n is equal to 1, and this is some fluid, but question mark, we don't know what it is. N is equal to, we don't know, but we would like to figure out what n is, so that's what we're trying to find. And the only difference that we observe is that the location of the first dark fringe to the right of the bright central fringe is y1a in the first case, and then something slightly smaller, y1b, in the second case. Okay, and the only thing that changes is the fact that we use a fluid with an index of refraction n. But as we remember, because we just did it in thin film interference problem, wavelength is contingent upon n. So if you start using lambda in air, that's fine, but if you throw the same lambda through a medium with an index of refraction n, then the wavelength is no longer lambda, it's lambda over n, right? So you got to be careful when you do this, right? We should, well, let me do this because, okay, I'm going to call this lambda air for consistency, and then I'm going to say lambda fluid is equal to, well, lambda air divided by n, so that's just lambda over n. Okay, but the point is that's the difference. But the screen distance doesn't change, the slit separation doesn't change, and so that's why the pattern is going to be different. If you have a smaller lambda, the pattern is going to be a little bit more bunched together, right? As lambda goes up, the pattern spreads out. As lambda goes down, the pattern comes in. And so if we're told that y1a is 4 centimeters and y1b is 3 centimeters, right here, then can we find n? Okay, very good question. So we have effectively a double slit interference problem. And we know then in the case of double slit interference, we have a formula for bright fringes and dark fringes. So we know where to locate them, so that's good. And what we're going to say is that, okay, if these are the two slits, this is the screen distance here, this is the screen, and you tell me that the first dark fringe is here, this is Y1A, let's call it. Right, this is for a certain angle theta. Then I can locate this dark fringe. I can find Y1A, in other words. Okay. Now, make a copy for this. This is going to be Y1B. It's going to be slightly less. Right. So maybe this is theta A and this is theta B, because obviously the angles won't be the same. But then in both cases, the screen distance is L0 and the slit separation is D0. Okay. Now, bright fringes. Let's start with the first experiment, experiment A. Bright fringes are given by D, so D0 in this case, sine theta m is equal to m lambda. Okay. And, oh, fine, that's good. For m is equal to 0, I'm going to get the bright central fringe, and I don't know what I'm doing. What am I doing? Apologies. You see, you get excited about bright fringes, and this is what happens. No, dark fringes, obviously. Right, we're looking for the first dark fringe. Okay, so I think what I had in mind was this, is that the center of the pattern is a bright fringe, right, called the bright central fringe. So let's say maybe it looks something like this, right? And then there's a dark fringe, and then there's another bright fringe. On either side, same thing. Okay. Well, the bright fringes end where the dark fringes begin, and vice versa. Okay, so if you want to find, where the first extinction is here, this is really the first dark fringe. And so for dark fringes, I'm going to say that D0 sine theta m is m plus 1/2 of lambda. And remember that it's lambda in this case, and it's lambda over n in this case. What is m to locate this guy is the question, right? Now, as long as this is positive, sine theta will be positive, meaning that the angle will be above the center line. And so it turns out that the smallest value of m that's going to yield a dark fringe is actually m is equal to 0 here. And then the next one is going to be m is equal to 1, 2, 3, and so forth, which is confusing because down here, the first dark fringe would actually be m is equal to -1, and then the next one would be m equals -2, and so on and so forth. So when it comes to these fringes, you have to be really clear what value of m corresponds to what fringe. And it depends if it's a bright fringe or a dark fringe because, well, the pattern is centered on a bright fringe, so it's fine. But that means that when you talk about dark fringes, m equals 0 is actually the first dark fringe above the center. M equals 1 is the second dark fringe above the center, etc. And so here I'm going to have m is equal to 0 means that D0 sine theta A is equal to lambda over 2, right? Which means that sine theta A is equal to lambda over 2 times d. Okay. Now, why do I want sine theta? Because it would appear that I need y1a, and y1a, I'm not going to get it through L0 and sine theta. I'm actually going to find that y1a I should say ym in general, is going to be L tan theta m. Right? If you look at the triangle that we have here, right, this is going to be theta m, this is ym, this is L0. If we're trying to find the location of one of these dark fringes, then ym is going to be given by L tan theta m. Okay, but we can typically use the small angle approximation, and we're typically told when we can use it. So if it's not explicitly stated, you might want to be careful. But in general, the problem says you may use the small angle approximation, and this one says that. Okay. Now, why am I told that? Is that, if I can use the small angle approximation, then y sub m is approximately L sine theta m, which is approximately, well, I should do this. Let's do this. Let's be clear. Okay. These are the angles that locate the dark fringes. These are the y positions that locate the dark fringe. You can give me an angle or give me y, but the problem gave me y, so I want to get my hands on that. So here we're going to say that, okay, for m is equal to 0, y1a is equal to L0 tan theta a. But we're going to say that this is approximately equal to L0 sine theta a, which means that it's approximately equal to lambda L over 2d0 if I plug sine theta a in. And the reason I can do that is the small angle approximation. So because tan theta is approximately sine theta by the small angle approximation. So it's nice because, yeah, I wouldn't want to arc sine this and then plug an arc sine into a tan. That's just tedious. So small angle approximation makes it a lot nicer for me. And I find that y1a is going to be this. Right? Now again, it's equivalent to locate fringes using y or using theta, because for a given theta, it's a given y, and so you're talking about the same fringe for a given fringe. But usually the formula we're given is this. This is geometry, so it's up to you. And then it depends what the problem tells you. But if the problem gives me y1a, okay, then I'll figure out y1a, and it's equal to this. Now, I've done this for experiment A. I can, just look at it and look at experiment B and say, well, the only thing that changes in experiment B is, of course, this is different and this is different, but it's because now I have lambda over n instead of lambda. So I can say now, just based on what I derived before, similarly, meaning with the exact same reasoning, I would find that y1b is approximately equal to, now careful, I need to use lambda over n instead of lambda. So this is going to be lambda L over 2n d0. And I want to solve for n. Okay? Well, I can do that, right? Look, I have this, I know what this is, and I know what this is. And if I look carefully, there's a few ways to do this. I could divide this by this, and I would get a bunch of simplification. Or I can say that, well, lambda L over 2d0, which is this, is really just y1a, isn't it? Right? So it appears to be the case that here what I'm looking at is y1a divided by n, effectively, which means that n is going to be y1a over y1b. Careful, flip that thing carefully. That's going to be 4 centimeters divided by 3 centimeters, 4/3, which actually tells me that the fluid is water, but even without recognizing that, that at least is the index of refraction of the fluid that I used in the second experiment. So, nice little problem about double slit interference. Most of these problems are just a matter of knowing whether you're looking at a dark fringe or a bright fringe, write d sine theta as m plus 1/2 lambda or m lambda. Then yes, you can derive y sub m from geometry, and you can use the small angle approximation typically. That might help you answer whatever question that you get. But it's very plug and chug, as I was saying before, right? We're not deriving anything complicated, right? We're not even deriving this, we're just using it. But I think it helps to see where it came from so that you know that what you're doing is accounting for a path length difference, just like you were when it comes to thin film interference. Okay, so let's wrap up and let's look at single slit diffraction with blue and orange light, which is a great problem. And we have, oh no, hold on. Let me do this real quick. Just, there we go. Just so that we don't have to redraw everything. Okay, there we go. Okay, single slit diffraction, what do I know? I know this. I know this formula for dark fringes, and I only know the position of the dark fringes, so there's that. I'm going to have a certain screen distance, a certain slit width, and the dark fringes are going to be given by this equation. All right. Now I'm told that orange light with wavelength of 600 nanometers and blue light with wavelength of 450 nanometers are simultaneously incident on a vertical slit of width 0.1 millimeter, and a square screen of 0.2 meter by 0.2 meters is centered a distance 2 meters behind the slit. Okay, so this is the middle of the screen here and here, so this is half of 0.2, which is 0.1, and we want to figure out at what location or locations measured from the central axis will the number of will light, wow. 2 seconds. Okay. At what location or locations measured from the central axis will a light sensor on the screen register zero intensity? In other words, where will you see dark fringes? State whether you are measuring horizontally or vertically from the central axis. Okay, so let's just start with this. Let's move this down for a second. You're shining light onto this slits. At the same time you're shining blue light, you're also shining orange light, fine. And you get this pattern on the screen that is going to spread out horizontally if the slit is vertical. Okay, so first of all, the pattern, to answer that question, spreads out horizontally if the slit is vertical. Okay, so that takes care of that. And we want to locate the dark fringes. Well, that's good because you know what? I know where dark fringes are when it comes to single slit diffraction. They're at angles that satisfy a sine theta m is equal to m lambda, where m is plus or minus 1, plus or minus 2, and so on and so forth. And in fact, rather than find angles, I probably want to find the y location, which, as we just talked about earlier, is given by L tan theta. So, the thing is, though, I am not just shining one wavelength through this slit, I am shining blue light and orange light at the same time, which means that if I want to get an actual dark fringe on the screen, it best be a dark fringe both for blue light and orange light at the same time. So I'm going to have to do some math here and separate orange light from blue light and only take the values of y that are common for the two. That's where I'm actually going to find a dark fringe. Okay, so dark fringes are given by this. I could also write that ym is L tan theta m. This is approximately, by the small angle approximation, L sine theta m. And if you were to find sine theta m based on this formula here, you would find that it's m lambda over a. So this is going to be m lambda L divided by a. And, well, here we go. Let's start with orange light. And then we'll deal with blue light. Okay, so lambda orange is 600 nanometers. Now, where are the dark fringes for orange light? Well, they're given by this, where lambda is lambda orange, right? So y1 is going to be, this is for m is equal to plus or minus 1. y1 is going to be plus or minus lambda orange L over a, which is going to be plus or minus 600 times a screen distance of 2 meters divided by a slit width of 0.1 millimeter. Okay, so 0.1 times 10 to the negative 3. I really ought to have this in meters, not in nanometers. Times 10 to the negative 9. Okay, and that's going to be equal to plus or minus 12 millimeters. Okay. All right. Let's continue. For m is equal to 2, you get y2 is plus or minus 2 lambda 0 L over a. That's going to be plus or minus, well, look, I mean, lambda 0 L over a is 12, so it's the same thing here. It's so 2 times 12, which is going to be plus or minus 24 millimeters. Okay, and we can keep going, yeah, because, okay, if it's going to be 3, then it's going to be 3 times this. Okay, 3 times 12 is going to be 36, so plus or minus 36 millimeters, and so on and so forth. Now we can continue on going, right? And we're going to eventually have to stop because we're going to run out of screen. So plus or minus 4, okay, y4 is equal to plus or minus 4 times 12 is 48 millimeters, etc. Now the question is, when do I stop? Well, I stop when I run out of screen, and I have 0.1 meters on either side. 0.1 meters is 100 millimeters, isn't it? So I can go here until I hit 100, and then I got to stop because I'm not going to see that on the screen. So plus or minus 5. Okay, this is a bit overkill, and it turns out that if you're good at arithmetic, you can figure out, you know, the least common multiple, and it's going to be a lot faster. But let's just do it the kind of the dumb way to, you know, show how you would think through this. y6 is equal to, well, 6 times 12, that's 72. Okay, we're getting there. Plus or minus 7. Okay, 7 times 12 is 84, isn't it? Yeah. Oh, you're going to have one more there. Okay, going to go all the way up to plus or minus 8. y8 is going to be plus or minus 96 millimeters. Okay, and then if you add another 12 to that, it's going to be 108 millimeters, but that's off the screen, so we can stop. We run out of screen past this point. Okay, and that's just orange light. And the bad news is blue light has a smaller wavelength, so we're going to have more values in the case of blue light, but it's okay. We can turn our brain back on at some point and figure out where we're going to actually get dark fringes. Okay, so blue light, lambda blue is 450 nanometers, we're told, right? And so, okay, for m is plus or minus 1, y1 is going to be, well, let's compute it at least once. It's going to be 450 times 10 to the negative 9 times 2 divided by 0.1 times 10 to the negative 3. So the exact same thing as this, just with 450 instead of 600. And this is plus or minus 9 millimeters. Like, ugh, joy. Okay, so then the next one, right, y2 is going to be 2 times this, y3 is going to be 3 times this, and so on and so forth. So this is going to be plus or minus 18 millimeters. And I'm going to go on until I find a common value with what's on the left. So 3 times 9 is 27. y4, it's going to be plus or minus 36. Ah, ding, 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 36 here matches 36 here. So at 36 plus or minus 36 millimeters, I get both a dark fringe for blue light and a dark fringe for orange light. So it is a true dark fringe in the case of this problem. So that is one location where I'm going to find a dark fringe. Now we can keep going, or we can turn our brains on. Okay, this is going to be the smallest common multiple of the two. The next one should be at double that, right? Should be at 72 millimeters. So you can continue if you want, right? Just keep adding plus or minus 9, and you're going to get, 45 and et cetera, 54, and you keep going, and eventually you're going to hit 72 again, right? So this is going to be plus or minus 45, plus or minus 54, plus or minus 63, and then plus or minus 72. And you're like, boom, boom, 72, that matches this. And then that's it, because the next one would be 3 times 36, but you fall off the screen, so you don't have to worry about that. This would be 108. And so the conclusion is that dark fringes are located at y is equal to plus or minus 36 millimeters, and y is equal to plus or minus 72 millimeters. Okay, so the question could have also asked, well, how many dark fringes are there on the screen? It's the same question, right? It's like, well, okay, to be a dark fringe, you have to be a dark fringe for blue light and orange light, and let's figure out where they are. And so here there's 4 dark fringes, right? Plus or minus 36 and plus or minus 72. But it's a cool question. I mean, it's a clever little question to deal with single slit diffraction, because, again, I mean, there's only so many questions we can ask you, right, when it comes to single slit diffraction. Okay, so as the slit size is continuously increased, will the number of zero intensity locations, in other words, dark fringes, found on the screen increase, decrease, or stay the same? Explain. And then as the screen is continuously brought closer to the slit, will the number of zero intensity locations found on the screen increase or decrease or stay the same? Okay, this is pretty easy, because let's just think about this. I mean, first of all, it's clear that if you make the screen bigger, or you bring it closer, then you're probably going to get more of the pattern on the screen, so you're going to get more dark fringes. And then the slit size, like, well, maybe that's not clear, but just keep in mind that, if you decrease the slit size, then y goes up, right? So if instead the slit size increases, y comes down, the pattern tightens. But the argument in both cases is the following, is that y sub m is proportional to lambda L over A. So what we're going to say here for questions 2 and 3 is that y sub m is m lambda L over A, meaning that y sub m is basically proportional to lambda L over A. So if A increases, ym decreases, and more dark fringes will appear on the screen. Because the screen has a certain size, but okay, if you bring y, if you decrease y's, you bring in more of the pattern, and so then you will see more dark fringes on the screen. Same idea, if L decreases the screen distance, then, well, it turns out it's the same thing. YM decreases and more dark fringes will appear on the screen. So that's not a very hard question. It's more of a conceptual question, which, of course, you can use formulas to convince yourself and justify your answer. But really the meat of the problem was here, figuring out that, okay, for a dark fringe to exist, it has to be a dark fringe for both blue and orange light. And so when we computed the different values, we just took the common values of y for which blue and orange light had a dark fringe. Anyway, so let's take a step back just to digest all that we've done. This is a pretty long one. We were talking about basically interference, either constructive or destructive the whole time. And we said that there are various, phenomena or experiments that you can carry out in physics in which it is possible to witness interference. That could be thin film interference, it could be double slit interference, it could be single slit diffraction. Okay, and for each one we went through and said, well, here are some formulas that either we've derived entirely from scratch in the case of delta x, that's for thin film interference, or we derived for double slit interference, but it was to make peace with, where does d sine theta come from and what does it represent? Okay, so we did that. And then we said for single slit diffraction, it's too complicated, we're not going to bother. But here's the formula for the dark fringes. We didn't even give a formula for the bright fringes because there is none that generalizes. We just said, hey, here are the dark fringes. So the point is, you end up at the end with equations that are pretty straightforward to manipulate. None of the math is complicated. It's just a matter of, is it hard to find delta x or not? And the hardest case is thin film interference. I would definitely recommend practicing that. I would practice it more if you have Speleo than if you have Bordel, because Bordel tends to like double slit interference more. Speleo really likes thin film interference. Of course, Speleo likes everything, especially if it's complicated. So I'm not saying don't study double slit if you have Speleo. Study everything and pray if you have time. But thin film is a little is not something that Bordel has typically done a lot of, if at all, in the past. So I think she did it once in the past 5-6 years. The point being, these are not things that are complicated mathematically. Once you get to the formulas, it's possibly deriving the formulas that is complicated and understanding what you're trying to do and what's going on. But if you spend a little time going through this and you think about it and you organize your notes and your formulas, you'll find that there's not that much in this chapter at the end of the day. There's a few technical things, but not that many. And it's much more plug and chug than having to think through, doing Ampere's law and superposition and, then changing magnetic flux through a loop because the area increases or whatever. It's far more plug and chug than that. And so it's a little faster to get good at interference and diffraction than other chapters like magnetism or induction. So in order of difficulty, I would say for the new topics, excluding what we did on midterm 2, optics is the easiest. I would probably say that interference and diffraction is the second easiest. The hardest would probably be quantum, although quantum is very plug and chug if your instructor is relatively reasonable. Quantum done by Speleo has sometimes been completely off the wall. So not so much recently, so that's good, but there's been a few problems that he's done in quantum that are just completely ridiculous. So that could be difficult, but the point is optics is super simple, interference and diffraction actually not that bad if you spend some time. Quantum is very much like interference and diffraction in the sense plug and chug. And if you get a reasonable problem, you're fine. If you get a hard problem, you just have to deal with the math. You can check out Speleo's old exams and you'll see. There's no physics involved, it's just math. And so you just buckle down and you do it. Or you skip it and you do other stuff. But
I would try to do it at some point. Anyway, yeah, that's about it. I mean, we have 1 week left. We're going to do quantum next week, and then it's going to be a wrap. And just make sure that, because the timeline is very short after Thanksgiving, as you know, make sure you spend enough time reviewing the older stuff too. You're going to find that going back to Gauss's law is going to be a trip after doing all of this stuff and going through induction and then waves and optics and all that. And you might not quite remember how to do Gauss's law. Now, it's not going to take that long to, get back on top of the ball and be like, oh, okay, now I remember how to do this. But it's been a while, and it's very different from all the things we've done recently. So don't neglect the first part of the course, because it is also part of the final. But of course, prioritize the newer stuff, because there's going to be more of that. So don't ditch all that to go review the first third of the course. But don't forget to spend some time on Gauss's law. It's a little tricky, but you can get back on top of the ball pretty quickly. Electric potential, nobody likes that one. And so going back to electric potential, that requires usually a little bit more time too. But don't forget to set time aside to do that, because it's easy to think, oh, I've already studied it and I'm fine. But it's been a minute, and there's a lot of stuff in 8B, as you know. So anyway, I hope you had a good Thanksgiving break. It is still break, actually, but that you enjoyed it. And I will see you next week for the final live stream on quantum. And after that, we will pretty much be, everybody's going to be heads down for the final, but it's almost over. You've never been this close to the end. So best of luck. You're almost done. And have a great weekend. Take care.